Okay, let's jump right into this explainer covering Lesson 5 of Evidence-Based Medicine for Techies. Now, if you're coming from a data science, engineering, or analytical background, medical literature can honestly feel like it's written in an alien language. But today, we're taking a completely different approach. We are going to look at clinical data through the lens of first principles and pure logic. We'll break down exactly how clinicians appraise diagnostic test studies, and we're going to do it using the exact same frameworks you probably use every single day.
To kick things off, I want to share a totally mind-bending statistic straight from the course's interesting insights. Imagine you've got a diagnostic test, a highly rigorous, scientifically validated medical test. Well, in one population of patients, a positive result from this test yielded an 8% predictive value, meaning if the test told you that you were sick, there was literally only an 8% chance you actually had the disease. But, and here's the crazy part, if you take that exact same test, run it the exact same way but on a different population, it yielded a 90% predictive value. So the massive question we have to answer today is, how in the world is this mathematically possible for the exact same test? The course relies on Socratic guided discovery, basically asking the right questions instead of just memorizing facts. So we're going to use that approach right now to solve this. We're stripping away all the medical magic and stepping strictly into the realm of pure probability.
Section 1. The Basic Toolkit. To solve this mystery, we first need to build out our diagnostic toolkit. We'll start by looking at a test's inherent fixed performance metrics, the baseline stats you'd see published in a medical journal. First up is sensitivity. Notice that word, inherent. Sensitivity is simply a metric of how well the test catches a condition when it's actually there. Say 100 people truly have a disease, and the test successfully flags 95 of them. Boom. That test has a 95% sensitivity. It's hyper-focused on snagging those true positives and making sure cases don't slip through the cracks.
Second, we have specificity. If sensitivity is all about catching the sick, specificity measures the test's ability to correctly ignore cases where the condition is absent. It's looking for true negatives. If 100 completely healthy people take a test and 90 of them get a clean bill of health, that's a 90% specificity. Think of it as the test's ability to not cry wolf. So sensitivity catches the positives. Specificity filters the negatives. But here is the kicker. Both of these metrics share a massive, glaring flaw when it comes to everyday clinical practice. They're calculated assuming you already know who is sick and who is healthy. You take a known group of sick people to find sensitivity and a known healthy group to find specificity. But wait, if a doctor already knows who is sick, why on earth are they running the test? That's just not how the real world works.
All right, Section 2. Real-world predictive values.
Let's pivot to the patient's perspective, where the answer is actually unknown. If you're a techie, you're going to instantly recognize this. A classic 2x2 confusion matrix. When a patient gets a positive test result, they really don't care about the test's overall sensitivity. They want to know, Doc, what are the actual odds that I have this disease right now? That is your positive predictive value, or PPV. It calculates the true probability of a patient being sick based on their specific result, looking at the ratio of true positives to all positives, including all those false alarms.
But here is the major plot twist of this lesson. Unlike sensitivity and specificity, which are fixed properties of the test itself, predictive values are absolutely not fixed. They are incredibly volatile. They shift wildly depending on who you are testing. A test doesn't just have one single PPV, it's completely dynamic.
Section 3. The Techie Translation. To really wrap our heads around why that volatility happens, we're going to translate these concepts into the native tongue of data scientists and engineers. I absolutely love this framing from the source material, evidence-based medicine in the language you already speak. You don't need a medical degree for this. You just map the clinical workflow directly into the analytical frameworks you're already using every day.
For example, doctors use things called likelihood ratios to figure out how much a test result should change their mind. Translated into your language, likelihood ratios are exactly the same thing as Bayesian updates. Before a test, a patient has a baseline probability of having the disease. That's your prior. The test result acts as a Bayesian update, shifting that baseline prior into a brand new post-test probability, your posterior. The test isn't giving you a simple yes or no, it's literally just updating your math.
Section 4. Trade-offs and ROC curves.
Of course, tests aren't perfect. Designing them means making some really tough choices on what clinicians call a receiver operating characteristic, or ROC curves. It's a constant trade-off, exactly like tuning a machine learning algorithm. Step 1, if you shift your threshold to maximize catching absolutely everything, aiming for 100% sensitivity, you mathematically have to accept Step 2, a flood of false alarms. Your specificity plummets. Step 3. If those false alarms are too costly, you shift the threshold back to prioritize specificity. But now, you risk missing true cases. You can't have both. You're always sliding a threshold up and down that ROC curve based on what's less dangerous, a false positive or a false negative.
Which brings us to Section 5, the missing variable, prevalence.
Okay, we finally have the tools to crack our opening paradox. We know about inherent metrics, predictive values, and Bayesian updates. Now meet the missing variable that explains it all, prevalence. Because likelihood ratios act as Bayesian updates, they have to multiply against a baseline prior. If the baseline prevalence of a disease in your population is incredibly low, like 1 in a million, even a highly specific test is going to throw off way more false positives than true positives. The math absolutely dictates it, resulting in that 8% predictive value. But take that exact same test into a high prevalence population, say an infectious disease ward where 30% of people are sick, and your starting prior is huge. That high prevalence boosts the exact same test up to a 90% predictive value. The test didn't change at all, the population did.
So, as you go back to building your own tools, I want to leave you with this thought. If prevalence changes absolutely everything about how a test performs, what happens to your algorithmic models when the real-world data doesn't match the environment they were trained in? If you train a model on a high-prevalence dataset and just blindly deploy it into low-prevalence real-world, it is going to drown in false positives, no matter how beautiful the math looked in the lab. So, keep your priors accurate, always question where your data came from, and ask yourself, are you optimizing for the lab or for reality?